Hello and welcome to a online version of Fun Times in Statistics, aka our class. So as you may know, I am doing a digital version of our Chapter 3 notes for today, and you just have to watch this whole video and you're good to go for Thursday. So I'm going to pick up where we left off from last time. So if you were in last class, we did some stuff with Minitab from chapter 2, but to remind yourselves, we're in the middle of chapter 3 and we just discussed the mean and the standard deviation. And if you remember, the mean was a type of center that determined where the middle was, middle with quotation marks. You can't see me doing that. Or center by using size, so it averaged everyone. So it was just the statistical version of what's an average. And then we looked at variance, which wasn't very helpful, but it was a type of spread that they used basically to try to describe the mean or how far things were from the mean, and that failed. And then we came up with the standard deviation, which was a better description of how the data was spread because it gave us average distance from the mean. Ooh, I was a little loud there. Hold on. Let me move my mic a bit. Sorry if that sound was terrible. Okay, so what we're going to do today is another center and some other descriptors of our data, and specifically some other spreads and other ways of representing what's going on with, our data, and trying to describe it. And this is personally my favorite center and my favorite spread because I feel like it works a little bit better, and I'm going to talk to you a little bit why. That being said, it might be my favorite, but it's not the one everyone uses, and it's definitely not the one we're going to use in the future when we start doing stuff in Chapter 7 and Chapter 8. So, although this is my favorite, I would say the mean is probably a little bit more useful, just so you know. All right, let's get this party started. So the first thing we're going to look at is what's called the median. The median finds the center of the data. Hopefully you can read this. Of the data by order. So what does that mean? It means that the median, I wanted this to say in the same type, but it didn't. The median, which we use the symbol capital M for, is placed so that 50% of the data is above M and 50% of the data, I'm going to have to fix this because it's not going to fit, is below M. So I'm going to hit enter right here because I'm going to draw a picture of this next to it. That's my plan. Yo. God, I'm so cool. Anyway, so the one thing you want to notice about this star, the median does not care about size. Unlike the mean, sorry. And that's worth noting because when you think about it, the mean only really cares about size. So if you have like really big values and really small values, the mean, so picture some like a data set that has only 6 values in it, and 3 of them are 0 and 3 of them are 100. The mean there is going to be 50, like right dead in the center. It doesn't have to be a part of your data set, and it really just cares about size. So if you had some values that were more on one side than the other, or, something that looks more like some of the shapes we're going to see later, you're going to notice that the mean cares about size, whereas the median just cares about position or order. Okay, so think about this as your 50-50, splits it in half, All right, and then along with that, we have another way of splitting this. So the quartiles, notice the word quart there, which stands for quarter, and that's really all about, hey, I want something that'll split it into quarters. So what do the quartiles do? Split into quarters. So be thinking like 25% pieces. But the way it does this is kind of interesting. Oops. So the first quartile, this is why I'm going to need a picture because this won't make sense while I'm writing it, which we call Q with a little subscript 1. Oh, and that doesn't come up as a subscript unless I make it. Gotta love technology right here. Oh, beautiful. All right. Splits the data with 25% of the data below it and 75% above. You're like, that doesn't seem right. I thought you said quarters. Just wait, I'll draw a picture and then it'll all be clear. And now I'm going to cheat because I'm, you know, it doesn't like how I spelled quartile. Did I spell it wrong? Oh no, I'm having all kinds of word errors. I want to copy this and then paste it. Perfect. And then I'm going to write, you totally think I'm going to write second quartile, but I'm going to write third. And you'll see why. And then, so this is Q, little 3, not 13. And it does it so that I have 75% below it and 25% above. So you totally saw that coming, right? That's definitely what you assumed what was going to happen here. You're going to see my menu here in a second because that's fun. And I'm going to go over here and pull out my drawing tool pen. And hopefully it'll recognize my pen today. And then I won't have to cut out 20 minutes of me fighting with it. So that'll be great. So if you picture your data, yep, it's doing good. Totally isn't recognizing my pen, so I'm doing this with my finger. I'm giving up, clearly. That was awesome. Let's erase that. Now, if you picture like a number line, and we're going to suppose that your data is like really simple, very simple. So it looks like everybody is just like real uniform and all the same. So it looks like a big brick. It's beautiful, isn't it? This usually does not happen, just so we're clear. Okay, so what the median's going to do is it's going to look at this like cake of evenness and just split it right in half. So this is where the median is. So I got 50-50 on each side, right in half. Perfectly even, unlike my picture. This is just as good as me drawing in class, isn't it? And then the quartiles are going to come along and be like, no, that's not enough information. Let's split it up even further. So here's quartile number 1. So then I've got 25% right here. God, I hope these pictures come through good. And then 75% above. I'm going to pull out my mouse and like do that again. 75% above. That's cool because it like made it so that happened. And then quartile number 3, this is just bigger and just live with it, okay? Draw your picture better than mine. Is going to be placed right here because then I've got the upper 25% right here. Good times. And then 25 right here. Woohoo. And 25 right here. Whee! So as you look at this, you'll notice that like, oh, it is like 1, 2, 3, because quartile number 2, as it's popularly called, is right here. It's the median. Woohoo! Totally saw that coming, some of you. It's a good time. So when you're looking at this, keep in mind they each split it into 25%. So when you look at the median, 50% below, 50% above. When you look at Q1, 325s above, so 75% above, 25% below. And then similarly for Q3, 75% below, 25% above. And so this is just another way of you organizing your data in a way that hopefully helps it make more sense. It's just keeping track of where things are. So what's nice about this is you could like take it and be like, oh, what's the middle 50% of like all of my, you know, students? How are they doing? And what are their scores ranging from? I once had a terrible, terrible math teacher who used this as a grading scale. So like upper 25%, above the third quartile, that was an A, right in here was a B, right in here was a C, and right in here was a D. And what was terrible about that is he would do it by where the quartiles are positioned. So if you had a bunch of people that were scoring like 99%, they might make up the upper quartile and be getting an A, and you at 98% might be right in here getting a B and pissed off the whole time. I really didn't like him. You probably wouldn't either though, would you? Had I not tick my mouth, because that was really loud on my microphone. All right, so the other way we can use this is we can use the quartiles to describe spread. So IQR is the interquartile range. And that's probably like the last time I'm going to use his full name, IQR. And it's the length of, or it's not a length, it's a distance, sorry. It's the distance from of the middle quartile. Ooh. This is about as good as when I'm writing in pen, you all get mad at me. So really, the formula we use for this is just IQR is, Q3 minus Q1. So looking back at our picture, the IQR, if you like, come on, is just how far is this distance? Right here. Oh, that's okay. There we go. It's beautiful and bright and strange and not what you. Oh no, I hit a button. Not what you saw coming, right? Good times. Anyway, so the 5 number summary is just a way of organizing these 5 characteristics together. Come on. There we go. And it's just a list of these together. So I'm being a little bit bad because I did not tell you the first and last number that are part of the 5 number summary because I'm pretty sure you know what this means. So when I write minimum, this is the smallest value in the data set. I didn't think that one needed a definition. And then we do Q1, and then the median, and then Q3, and then the maximum. Again, maximum I didn't think you needed a definition for, but it's just the largest value that occurs in your data. So when you're looking at this, it's just a way to organize those 5 numbers describing that brick I just showed you. Now, when you look at that brick, again, I was assuming all my data was nice and uniform. So if I had, you know, more lower scores and more higher scores, it would be spread out in different directions. And we'll see how that works when we start doing some examples using the 5 number summary and the visual version of the 5 number summary, which is known as a box plot. You may know it by its other name, box and whiskers. Kitty, kitty, meow. All right. I hope you don't hear any of my birds yelling in this, because that would be, well, kind of funny. Anyway, so I'm going to zoom out a little bit for this one. Good times. Alrighty. I just burped. I'm sorry. So here's some data. It's a good time. And what we want to do is we want to find the median, the lower quartile, the upper quartile, and then the minimum. So the first thing you'll have to do is, since order matters with all of these calculations, is we'll need to put it in order. So you notice this is out of order because you might think it's an increasing order. You're like, oh, 110, then 125, it's getting bigger. Oh, wait, 99, that's smaller. So let's go ahead and order this appropriately. So first up is 85, then 95, then 99. I really should put bigger spaces here because it's starting to look like these all run together. And I want order to look like it's ordered, right? And then I have 110 twice, so I got to be careful because I do need to list it both times. And then 115. I thought there was one lower than 115. I'm wrong. There's 119. That's the one I was thinking of, which is definitely bigger, just in case you didn't know. 125. And then 132. I think I'm drier on the videos. I just want the spacing bigger so you can see the numbers are separate. I should have used commas, but I don't like using commas, especially for our international students, because in some countries what they use for period we use for comma, and what we use for comma they use for period, and I don't want it to be confusing. And then so now it just looks like a big, really poorly written number. That's fun. Anyway, so when I want to find the median, what you need to find is the center. So there's a couple different ways you could go about this. You could look at this and be like, how many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So the middle would be the 5th one, since 5 would be the position that's halfway in between those two. Or you can think about it as, oh, if I want to split 9.5, that's 4.5 on each side. But that doesn't make any sense because you can't have a half, so I'm going to have 4 on each side. Or you can do what I do, which is I just kind of count my way towards the middle. So put your fingers on the screen, which you can't see me do this, and start at 85 and 123, and just move your fingers in one step on each side until they touch. So you're at 85 and 132, you move into 95 and 125, and then 99 and 119, and then 110, the first one, and 115, and then you nail yourself into the center at 110. So I'm going to draw on this again because that's going so well previously. So you notice that right here, the second 110, and it's important that it's the second one, that went really well. There you go. That's going to be my median. Fun times. So M is 110. Cool. So you'll notice that I have 4 below and 4 above the median. So when we go to calculate the lower quartile, I'm going to be looking at, woohoo, these 4. And just finding the middle again. So one of the problems with this is you'll notice that There's no place for your finger to meet in the middle because you'll start out at 85, 110, 95, and 99, and then there's nothing in between those two. So what you do when that happens is you just average the two values that you're touching. So my Q1 is going to be 95. Oh, that's a beautiful 5 plus 99 over 2. Oh my goodness gracious. How bad is that 5? Let's just talk about that. If you've never tried to draw with a digital pen, welcome to my world. It's not working. I've been trying to use my finger and my mouse. It's good. When you average those, you get 97, which I'm hoping you notice lies completely in the center of these two. So right there is my Q1, and I'm writing over top of that, so that's beautiful at 97. And I'm going to caution you, those of you who like to use Excel, how Excel calculates the quartiles is different from how a lot of programs calculate them, so you got to be careful. And the same thing with the calculator, it will do it a little bit differently. There's not a real consistent way this is always done, so be careful. Yeah, that's the only warning I have about that. My suggestion is always use Minitab since that's what we're using in this class so that you always get the correct answer. All right, so then for quartile 3, we'll have the same problem. We'll have 2 that are in the middle, so on the average of these two. So quartile number 3 is going to be, I'm going to add 119 plus 125 and divide by 2. So notice I'm just averaging those values, not all of the values, to get 122. That's a beautiful written value. Hopefully you're listening to this with sound. I had someone tell me, yes, of course I have the sound on in my online class. Of course, I mean, you could kind of watch this without sound, then you wouldn't have to hear my annoying voice. Maybe I should get someone else to do my voiceover. Now I'm overthinking this. Let's scroll down and find the minimum. Yay! So who's the smallest? 85. Who's the biggest? 132. These should be the easiest things. Although drawing an 8 seems to be something that I have difficulty with. Woohoo! Alright, so then I just need to organize these into my 5-number summary. So it's going to be 85, comma, and this is how we write them. It's a little weird. 97, because that's my first quartile. I got my minimum on there. 110, that's my median. Then 122, and then 132 for my maximum. Cool, and now we're going to create a box plot for this data. So once again, I'm going to be pulling out my digital pen and drawing you a picture. So I haven't told you what a box plot is, but I have told you the other name for it is the box and whiskers plot. And it's a way for you to plot the 5-number summary and represent all the data in a way that you can organize it and hopefully visualize what's happening and get an idea of how the data looks. Because what we're going to focus on next is, okay, now that I have some centers to describe this and some spreads, what else can I describe about the data? Because knowing where the center is, the average or the median, and how it's spread, the standard deviation or the IQR, doesn't really tell me what the data looks like. It just gives me some idea of what some values might be. Here we go now. So what I'm going to try to do is, hold on. Oh, this is going to be about as exciting as I thought it would be. There we go. Beautiful straight line. And I'm going to make this a number line, so I'm going to, come on. There we go. It thinks I want to scroll for some reason all of a sudden. It's not recognizing my pen. Yep, it's a good time in Rochelle Land. Here's 80. Yep, still thinks I want to scroll. I am drawing a picture, sir. We'll call this 80. Okay, this is the worst thing I've ever tried to do. I'm going to have to cut part of this out because it's just not working. Okay, recognizing the pen. Nope. Let's try the other pen. That's always worth a try, right? I do have 2 of them, which I find mildly hilarious and sometimes confusing. Word is the worst with this. I really should have chosen OneNote. It works a little bit better. 90. There we go. Now we're running with smoothly. 100. 110. In a perfect world, these would be perfectly spaced, and then this would be nice and easy to see what's happening. But we're going to get a decent drawing off of this, I promise. This last one's too far. Should I try and erase? Yeah, let's do this. Whoa, no! That's okay. I believe in my ability to not... Okay, that's just as crooked. Good times. Okay, so now what I want to do is draw my box plot. So the way this works is you usually start with your minimum. This is the way I like to draw them. If you don't like this by the end, it's okay. And I'm just going to put a little line there, a teeny one, so it's at 85, so I want it halfway between these two. Put it right there. Now I'm going to put in my maximum. It's 132, so I want it just a little bit bigger than 130. Little line. And then I'm going to throw in my middle parts. So I'm going to throw my median and my two quartiles. I like to do the median first. It's right at 110, which is kind of nice. And make that line just a little bit bigger. And maybe a little straighter would be good. Let's be honest. It's going real well today. Oh, so much better. Okay, good. Oh, and now I'm going to put in my max. Sorry, not my max, my Q3. So it's just a little bit bigger than 120. So I'm going to put it right here. And fill out my box, my first one. So this box is representing the 25% of data that's between the median and the third quartile. And then I'm going to draw a little line out here. This is what's called the whisker that leads out to the maximum at 132. And hopefully you notice that these look about the same distance, which is exactly what's happening. And then I need to throw in my, come on brain, my lower quartile, quartile 1, which is over at 97. So I'm going to put it right here. Here's the second part of the box. And then the lower whisker, which goes from the minimum to the curved at the end, the Q1. So this just represents the data. So hopefully you've noticed that this looks relatively symmetric. It's only off by about 1-ish in the distance. So both sides look about the same spread. Now, if one of my sides would have been longer, that means that the spread amongst my data in that 25% would have been further away or further spread out than the rest. So we're going to see some ones that aren't nice and symmetric like this one. This one's pretty good because pretty much all my distances are the same. So this is 97 to 110. That's a little bit longer. Actually, that's quite a bit longer. Yeah, that's like 23, whereas this one's only 12. Yeah, that's more spread on this side. So that's what this is telling me, is that it's almost symmetric, but my left side is a little more spread out. So we're going to see that that means that I have a little bit of what's called skew on the left side, where it's a little bit more stretched with your data, or more spread out. Because we're going to start talking about shape next and describing our data. But I have to teach you one more picture before we can do that. So moving on up to another picture. God, I'm annoying. Alrighty. I'm sure when you got to the and you were like, I really hope she's not going to make us do things with this. Oh no! She totally is, because that's who I am today. Woohoo! So we're going to make what's called a histogram. A histogram is probably the most popular graph in all of statistics. So bars give you frequency, and they can touch because values are right next to each other. So this is made up of bars as well, but it is not a bar chart, because bar charts are reserved for categorical data only. So bars, bar heights represent frequency. Just a little reminder, the other name we use for frequency is counts. Oops, missed my end parenthesis. And when you're looking at this, bars will be able to touch because the values will, that's not how you spell will, they'll be right next to each other. That's also not how you spell each other. That's a word I frequently have a hard time with. It's like my version of a lot. And then my little warning for you with this one is this is not a bar chart. Those they can't touch. Man. And are for categorical data. Histograms. are quantitative. Good times. So what you would do to figure out what this one looks like, and I'm going to have to zoom out a little bit for this one as well. There we go. Is you'd go through, and I've got these GPAs. These are from a sports team at one of the universities I was looking at, where they do like competitions to see who has the best GPA, and they take turns getting this award when the team's carried around, and it's kind of fun. I think this is their women's soccer team. Nope, this is way too big. I think this is a track team. Yep, okay. I don't think it's ours though. It's just one I found. Anyway, so we're looking at their GPAs. They're looking pretty good. That's a good time. And what you would do is you'd take the counts and you'd separate them into different groups. So I've made 6 groups here. So these are called classes. So I took the lowest value, 2.9, and went up to something that I knew would exceed the maximum. And I chose to make them about 3 apart. So 2.9 to 2.1. So if you're in this range, what you would do is you'd count to see how many of the values fall in this range. So there's 1, 2, 3, 4, 5, and this one's too big, so there's 5 of these. Woohoo! Good times. I say that too much. Anyway, and then you do this next grouping, and so 3.15 would be in there, all the way up to 3.3, and then you'll notice the person at 3.33 will go into the next grouping. So I went and do these ahead for you. And if you want to double check my work, you can go through and count them, because that seems like a good use of your time. This isn't that difficult. Ooh, not 11, there's 16 of those. 20 and then 8. So I like the way this one looks, by the way. I think it looks very interesting when you do its graph. Alrighty. So then next up, I'm going to go back to using my pen. Just oh so successfully. Awesome. And I'm going to draw in my axes right up here. So down below, I'm going to have my GPAs. So this is going to be 2.9, 3.1. You can tell when the pen's working and I'm not using my finger because the writing actually looks good. 3.5, 3.7, 3.9, and then 4.2, although no one has a 4.2 because that's not possible in college. And then I need to just make my frequency on the side go tall enough to where I can hit 20. So I'm going to do 5s because I'm feeling like that's going to work. We'll see. That's the worst 15 I've ever written in my life. Please feel free to judge me for that one. Okay, I'm going to switch over to blue to make my bar height since I did blue for the text for this. So there are 5 here, and then 9, so just shy of 10, and then 17, and then 16 is just a little shorter, and then 20, and then 8. So I need that to be lower than the 9, so right about here. There we go, and that's a histogram. So what I really need to do is get this a title. So normally we'll be like, this is the histo of GPA. Oh, that's just the worst thing I've ever written. Good times. And obviously I really should label this frequency or counts. Let's see if I can get this done without ruining everything. Oh, that's decent-ish. So this looks a lot like a bar chart, but again, notice it's touching because 3.15 and 3.10 are right next to each other. So the fact that they are touching and this one looks like it's not touching, sorry about that, has meaning. There's a lot going on here, man. A lot going on. These are right next to each other. This also means that if you have a gap or a place where there's nothing, it means that there is no data that has those values, just like we saw with some of our relative frequency charts. Speaking of relative frequency, hello transitions. Let's go down and do this for relative frequency. So what you would do for relative frequency, and this one's actually pretty easy, is it's the same idea, only I would take my counts and divide it by the total. So as you're looking at, oh my, I'm gonna have to cough, hold on. Sorry about that, I had to pause so I wouldn't cough in your ear. What you would do is you'd take your 5 plus your 9 plus your 17 plus your 16 plus your 20 plus your 28 and add those all up and realize that you have 75 students. Another way you could do that is you could scroll up here and realize that this is a 1, 2, 3, 4, 5 by however many that is and multiply and you'd get 75. So there are 75 students. So to do relative frequency, you're going to take your counts from each class and divide by the total. So for instance, to do this first one, and I'm going to draw this with a pen, you would do 5. Come on. She's not catching up to me. Come on. Draw for value that goes in here would be 5 divided by 75. Yeah. Where 75 comes from, because I said this and didn't write it, that's a 16. That's awesome looking. Okay. So, I'm going to fix this really quick. Hopefully. Nope, I'm not going to fix it. I'm going to make it worse. All right, so I'm going to type some values in here that are going to represent where this is coming from. But I'm hoping you realize that this just is relative frequency. You take the total and you use it to divide up your individual values. So I did that ahead of time to make this easier on you. So I'm going to put what those values are in here. But you should, if you have a calculator on you, pull it out and follow along with me. So you should get 0.66. I'm going to round these quite a bit, or where necessary. Some of them come out nice and even though. 66.2133. Those are the ones that don't come out so nice. Well, actually, I shouldn't say that. There's a lot of them that don't come out so nice. Haha, I have a lot of 6s there. Scary. 0.10. Okay, I rounded that one correctly. I didn't round this one correctly. Or this one. There we go. That's better. And then you would graph those values. So I'm going to graph the percent instead. Or sorry, I didn't do percent. I have to multiply by 100 still. This is what I get for just being like, oh, this part's easy, right? Wrong, teacher lady. Those of you who are in pen, I apologize that it took me this long to fix this and write it correctly. I even looked at my notes. Make sure you use percents, not decimals, is on there. Good job listening to your past self. Oh, man, she gives me such good advice and I never listen to her. Anyway. Alright, so what we're going to do is we're going to graph this next. So I need a pair of axes again. And it's not going to want to listen to me this time, so we might be stuck drawing with our finger again, which we saw how successful that's been in the past. Oh, come on. Now it thinks I'm trying to mail something. If you could only see what it was doing on my screen. You can only see what I'm writing, which is kind of weird. Neener, neener, neener. Nope, I want the pen. Aha! Got it. Oh yeah, that's so straight. So I'm going to have the same scale. 2.9. I'm going to try to fit it in here. 3.1, 3.3. 3.5, 3.7. Oh, so pretty. No, wait, I did 3.5 twice. That's awesome. 3.9 and 4.2. In my dream world, these two were just right below each other, so this was super easy to see. So I'm going to do percentages, and I'm going to be real lazy and do like 10, 20, and then 30%. And I'm just going to use a different color for my heights. So this first group is 6.5%, so slightly bigger than half. This wobble I'm going to ignore and just treat this as being like 0, you know? And then 12% will be a little bit bigger than 10. 22%'s got to be bigger than 22. 21 is just a little smaller. Whoops. 26 is the biggest one here. There we go. And then slightly bigger than 10. Okay. And then real quick, compare these two. They have the exact same shape. So whether or not you want to do frequency or relative frequency is completely, entirely up to your choice. Yep. Cool. All right, box plots. Good times. So we did a box plot previously, so I'm going to be a little bit lazy when it comes to this one, just so that we have it down for a second one. The big thing with box plots that I'm hoping you notice is that it represents the 5-number summary. So real quickly, I'm going to write the 5-number summary because I calculated it earlier. 2.9, 3.4. Okay, I'm not going to lie. When I say calculated, I typed that data all into Minitab and had Minitab do it for me, which is totally what I'm going to show you guys how to do on Thursday. So get excited because it is much easier than trying to do it by hand. And my max is 4. So I'm going to do my number line down here. Rather suggestively, I'm going to use a similar scale to what the previous one has. So I'm going to start at 2.8 and just go up by 2s. Just because it sounds easy. Oh, I'm going to run out of room. No, I'm not. I'm going to make it just barely. Woot woot! Alright, a red one for fun. I haven't used red yet. So my minimum, my maximum, and then here's my first quartile. Here's my second quartile, because I did the median. And then here's my third quartile, and then boom, daddy, there's my whiskers. So you might look at this box plot and be like, oh my, that minimum is super far from average. I wonder if that's unusual or not. And this is actually a really common question in statistics. When I look at my data, how can I tell if my value that I'm looking at is unusual? And we are actually going to give an answer to that question today. Or actually, it depends on how long this recording takes. It might be Thursday. I need to not giggle so much because it comes off really loud. I think it's funny. Okay, so, and the other thing is, like, this IQR, looks pretty small. Like, the distance here is not very big, so this seems kind of far away. You might ask yourself, is this unusual? Is it extreme compared to everybody else? Extreme. And we're going to look at some ways to see that. The first way we're going to look at this is what are called outliers. So I'm going to give you a bit of a definition here, and then we're going to calculate it. So that's fun, because that's what we do, is math. So outliers are values that are considered to be extreme compared to the rest of the data. That's not what I wanted to have happen. Why is this italicized? I did not do this. Okay. I guess we're going over here. A value that is extreme compared to the rest of the data. Woohoo! And it's just, you can have many outliers. You might have some on the top, you might have some on the bottom. It's possible to have quite a few. So the way we're going to describe outliers here is different from how it's described for other data types. So don't think this is the end all be all only way you find outliers. There are actually a couple different other ways. But for quantitative single variables, so just one of them, because we're going to see the double variable version in next chapter, the way we do it is if you are if above, and the way this looks is Q3 plus 1.5, so 150% of the IQR. Woohoo. Or below Q1 minus 150% or 1.5 of the IQR. And I'm going to do it for the one up above so you can see what this looks like calculationally. So we consider any values that do that are outliers. I didn't want this to be spaced the way it is, so I'm going to run out of space if I don't do that. So the first thing I'm going to say is I want to find, is it 150% farther than the third quartile? So think about like this width here, that's what the middle 50% of my data is, that's how far apart it is. And so it says, looking at the quartile number 3, it's more than 1.5 that distance, so like 1.5. So being 1 of that distance away, that's your middle 50%. That's being bigger than 50% of your data away from that center line, which seems extreme. But using 150% or the 1.5, it seems like it's even checking for more extreme than that. So just keep that in mind. All right, so I'm going to actually calculate that for you. For this data. So the first thing I'm going to note is that here when you look up above, note the IQR, because I'm going to need this in a second, is my third quartile. Oop, 3.8 minus my fourth, my first, there is no 4, 3.4. It's because it's got a 4 in it. It's messing with me. And that's just 0.4. So I'm going to use that in my calculation. So to do the upper part, I'm going to say, hey, is it above? Come on. Nope. Q3, which is 3.8, plus 1.5 times 0.4, which I just found because that's the IQR. And if you do that multiplication and then addition, you get 4.4. So that means that I'm good because the biggest value I have here is 4, and if it's above 4.4, that's when it would be an outlier. Nothing does that, so I'm good. And then my lower end, my below, is going to be 3.4, that's my first quartile, minus 1.5 times 0.4. So just keep in mind the IQR, that's where that 0.4 came from. And then you do your subtraction, and you get 2.8. Woohoo! There we go. So this 2.9, or the few people that got 2.9, because there was a couple of them, are just barely skating into the safe zone, you know? Because 2.8 is where we make the cutoff for when it's going to be unusual. So if I had somebody who had like a 2.5 in this data, that would be an outlier. All right. Now let's talk about how to describe shape, or how your data be looking. So these are all verbal. So we look at usually a histogram and then make this decision. Why is my voice so bad today? Whisper, whisper, whisper. All right. So the first thing we're going to look at is what are called modalities. Modalities are the most frequent values in the data. Woohoo! So you maybe knew this as the mode back in your day, perhaps, you know, depending on where you had your education. It's, you know, different for different people. So that's what it is. We now use the mode as a verbal descriptor of how our shape looks. Yep. So unimodal is when you have one most frequent value. Oh, I missed something up here. Most frequent value in the data, these are called modes. And I'm going to put the S in parentheses because you might not have more than one, as we just saw, just one. And then here's me just being a jerk. Uni for 1, which you already know. Bi, we reserve that for 2 because we've seen this before with other data like bivariate. That's super lazy. And then multimodal is just anything that's going to be more than 2. Yay! And these need to be plural. Good job, teacher. You don't teach English, though, so I don't know. I should still, you know, represent good practices. All right, I want to draw some pictures of this. So if you're picturing like unimodal, there's lots of ways this could occur. It could be, you know, I'm just going to draw some mini graphs of a couple of these, you know. So unimodal is like, oh no, my data is short, and then I got one tall one. That looks inappropriate. Or maybe it's this value that's really big, and then only a couple that are like really small over there. And then bimodal, this is like what I would consider a disaster. Dun dun. It looks like fangs. Good times. Or, oh no, the worst grading distribution ever. Lots of people got low, and then lots of people got high. Remember, this is quantitative, you know. Like this one, like I terrified. Like, what did these guys do to prepare? You know, what did these guys do? What's different? I don't know. I feel like I'm drawing power plants. That's what it looks like. And then multimodal, like, this is one of my favorite multimodals, is ones that look like stairs, because they're really hard to model and do things with. Because they have what they call jolts in them, where it suddenly goes up. You know, that's what your electric system looks like. Is suddenly things will go up because things get plugged in, and then it goes back down to normal for your regular running things. That's really hard. Good times. I don't know. In math, they're really hard to model. I'm not drawing a third one of that one because this is getting dumb. Anyway, so that's our first sort of like, what does it look like descriptor. Let's move on to our next one, which is shape. So this is going to be overall shape that we're looking at, not like what's the word I'm looking for? These are, use your best judgment. So a distribution or graph that we are looking at is going to be uniform if the data looks like roughly all the same value. So be thinking like all of my boxes or all of my bars have the same height. This means there's no peaks. And then for fun, an extra 0. We call it symmetric if the two sides split. Oops. Oh, I can't spell that word today. By the center are the same shape. And then the last one I'm going to do separately. I'm going to type it in here because that's who I am today, so I have to move my clock somewhere. So skewed is, it's not doing, it doesn't want to do what I want to do. One side, nope. Oh, I'm loving typing. One side has most of the values. I shouldn't say that, has a majority. With a few values on the other side. And I'm going to go into way more specifics with skewed because it's a little more complicated than the other two. But I'm hoping you're already picturing what these first two look like. Come on, pen. Let's draw us some pictures. Do. So uniform. This is going to be hard to describe. Like, it looks like bumpy cake. You know, like everything's kind of roughly the same. That's the smallest bar ever. Sorry about that. Oh, I could just make them all small. Winner, winner, chicken dinner. I figured this out. I feel like so special. So like they're all about the same height. So you're going to see some variation here. So if you're trying to picture why you might get something that looks like this. Like, imagine your two friends are arguing about whether or not a dice was fair, and so one of you takes it home and rolls it like 100 times, records how many 1, 2, 3, 4, 5s, and 6s they get. That's what this would look like. It should be all about the same if the dice is fair. But, you know, rolling it 100 times, sometimes you'll end up with more 6s or more 5s. Maybe you just happen to get fewer 4s, you know? It's something that's possible. P.S. That's totally how we ended up with people making dice that look different to try to make them more fair. Because it doesn't, 5 and 6 tend to come up more frequently if you pip them, which means you drill holes into them. Yep. And then symmetric is the two sides look about the same. Now, the big mistake people make with symmetric is they assume all symmetrics look the same. Come on. Why can't I get a second line on here? Nope. Pen. Black. Line. Haha, winner. Okay, that's fun. Nope, red. Red. My screen is screwing up. This is not good. Oh no. Oh no. It's trying to lock and highlight and do other things at the same time. Okay. So my two sides just need to look about the same. So I did this one earlier, but I'll do it again, but with the pen. I love it when my bars are the same height. Or sorry, not the same height, but same shape. It's like about the same on each side. So I made this one a little taller, so like about the same. Here's the like super popular one that most people picture when they picture symmetric. Trying to meet the bottom doesn't work so good. You know? Like big thing in the middle and then some stuff on the side sloping downwards. Boy, that's fun. I want to select nothing. Won't let me. Alright, so let's talk about skewed. There are two types of skewed. There's skew right and there's skew left. So how these look is different. And hopefully you're not like me and you don't have a hard time telling your left from your right, because it does make this slightly harder to do. I love when my boxes are slowly but surely starting to get rounded on top. Ta-da! Okay, so as you look at this, pay attention to my mouse, which hopefully is getting recorded here. Select objects. Um, on this side, like most of my data is over here, and then I've got this little bit of extra guy coming over here, and a little bit of extra guy over here that's on the left, and then most of my data is over here on the right. So if you're paying attention to this, like I think of it as dinosaur fun time. Like if I was to draw this as like, you guys remember the dinosaur with the big old fin on his back? That's this one. So like here's his head, you know. Nom 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 nom. It's hard to believe I used to teach art. Here's his back, and then over here is his tail. It's the tail that tells you the direction. So figure out where the tail is. That's where, you know, it's going to be dinosaur time. I don't know why I'm doing this. It's not letting me draw dinosaur heads anymore. That makes me slightly sad. Just slightly, because as you can see, my artwork here is just fantastic. This should hopefully give you some appreciation if you've ever read any online like art stuff about drawing with a digital pen. It's hard, yo. Well, I mean, mine wasn't made to do this, so I'm just forcing it. Anyway, so if you're trying to think of things in the world that look like this, if that helps you, like where's a real world application of this? The data on the left, which is skewed right, wow. This is got some really easy examples. I'm saying too much. So usually this is like company salaries. Come on. Nope, not letting me draw that. That's great. Try it with my mouse. Oh boy, I'm ready to give up. Because if you think about it, there's most companies, we have a couple people that make around the same amount. Maybe these are like my interns over here on this first bar. And then we have just a few people making more, the managers and the COOs. Or the C positions as they call them. And then my joke for this left distribution is there's not a lot of things that have the skewed left distribution in nature that come up naturally. The skewed right is actually way more popular and way more common. My one that scares me with this one is grades. You know, most people make like around the same grade, and then you have this group over here, which I lovingly call the missing. You know, they go missing halfway through the semester, you forget they're in your class, and then they show back up. Usually with no explanation, which is also kind of fun. You know, I always wonder where they go. I hope it's to other classes, so they're at least getting something out of the experience. Most students over here. Woohoo! That's a terrible example. I judge myself for using that. All right, let's go on. So now that you know some of this, let's do some examples. Use the histogram below to answer the following questions. This should go smoother because I can write things now. Good times. So write a description of the distribution in terms of shape, center, and spread, and any unusual features it might have. So when I'm doing this, I always start with the verbal components first, and then I go to center and spread and unusual. So I would say that this one clearly has one peak. I'm going to call it unimodal. With a, let's see, shape-wise, looks pretty skew right to me. Unimodal, comma, skew right, with a center at about, and here's where you got to be careful. So if you want to do the mean at this point, you got to kind of picture like where things would balance on here, and that's a little hard to do. So with me, I like to do the medians for this because I can more easily picture in my mind where I think it would balance area wise. So like if I was to paint these with the same paintbrush using the same paint, where would be the halfway point to where I would use the same amount of paint on each side. So I'm going to call that 102 roughly. It's probably closer to 101 actually. So I'm going to leave that on there. And I'm going to say the spread is about, and you're estimating here, so use your best skills. I'm going to call it about 6, because that's what it looks like roughly to me for the standard deviation. And possible, and here's where you're going to get real maybe mad at me, because like you're noticing I'm using words like about and roughly, and we're trying to describe it as the best we can for the attributes that we have. There are some values on the upper right end that are pretty far away from everybody else. So I'm going to say there's some possible outliers at around 116 because they are kind of far away from the rest of the data. What you should do is you should pull out your technology and pull out the data rather than just looking at the histogram at this point and ask yourself, hey, is this above 150% higher than quartile number 3 using the IQR? Cool. Here's the fun question. Which number would you expect to be larger, the mean or the median? And you might think, oh, there's no answer to this question, in which case you are completely wrong, unfortunately. As it turns out, it's actually really easy to tell. And the answer has to do with looking at outliers and extreme values. So I look at this and I immediately see, oh, this is skewed right, which means I have more values that are large compared to the rest of the data. So I have several large values that are extreme or possibly like farther away from center than most of the data over here. But those and their size is going to matter to the mean because the mean cares about size. They're included in the average, whereas the median doesn't care about where they are as far as size goes. It just cares about what order they fall in and where the median might be. So that means the mean actually is going to be greater than the median in this case. Oops. So this is also a way you can kind of detect skewness, is you can see that the median is greater than the median when you calculate them. And we'll see this when we go into lab on Thursday. So another way that you can picture this if you're having a hard time imagining it, like picture our class and everybody in it, and you are going to look at everybody's height and then take the average. The average is probably going to be around like 5'7", 5'8", something like that. And there might be one or two of you that are exactly the average in this case. And then when you look at the median, it's probably around the same value. It's probably at 5'7" or 5'8". And you can probably picture out which classmate is probably the person it is that height. I apologize if you're my class that has more sports people in it. It's probably taller for your class. Just saying. Tall people in sports. I got cut for the volleyball team for being too short, not because I was a bad player. Motherfuckers. Ah, crap, now I swore on this. Hopefully YouTube won't dock me. Anyway, so when you're picturing this, we've got all of our class together. We're all around the same height, Well, not all around the same height. There's some variation there. There's different heights for different people. But our mean and our median are pretty close. Now we're going to pretend we're in Harry Potter land and we're going to get a new classmate and that person is a giant and they're 10 feet tall. So when we add them into our class when looking at the height, think about what that's going to do to the average. It's going to add in a really big value. So that average, that mean, is going to get pulled towards those really big values, just like it did here in the graph. Like, oh, I've got most of my values around 100 to 104, but I've got these extreme values pulling the mean bigger than the rest of the data. What's going to happen in the median? Well, it's going to move over one slot because it only cares about order. So it probably won't change at all if it changes. Like, it might not change at all. It might change very little if it does change. So the mean is more affected by extreme values. So when you have skew, the mean gets pulled towards the tail. All right. Now, which box plot? We've already said skewed right, so we got to be careful. We got two choices here. This guy or this guy. So the first thing you probably notice is, let's look at the median. And I look at this center line and I notice, that's way too big. It's like at 106. And you look back here and you're like, oh, 106 is like here. There's no way that's the median. So that's the first problem with number 2. The other thing is when you look at the box and whiskers here, the whiskers are about the same size and the boxes are kind of close on each side. So I'm looking at the third quartile box, the first quartile box. Obviously the first quartile box is bigger, but my two whiskers are about the same size, which means this is relatively symmetric looking. That don't look symmetric to me. So pretty much this is pointing towards, let's look at IIE. That seems to be the right one. in all indicators from what we see. And then you look at this one, you're like, okay, is the median in the right spot? Yeah, looks pretty good. And then it's got possible outliers right here, and these get marked with stars. It looks like II is our correct one. Oh no, the circling of that went terribly. Oh, so good. I love the pen when it works. There we go. That one is the correct one. Huh, that's bad. Okay, let's look at another one. Oh no, what shape could this one be? Let's find out. Um, so as you notice, the bars are all about the same height. They're all around 7. So I'm going to go ahead and call this uniform. Oh, come on. All I want is this pen to work for once. Let's give up and try the other pen. Let's make noises that will make people not want to listen to the rest of this video. Okay. So this looks pretty... this looks pretty uniform. Give up and type. Okay, teacher. I don't think this is going to let me type on this. I really don't. Yeah, it's taking me to the bottom page. So this one we'll just do verbally, and hopefully people are listening. So this looks pretty uniform to me. All the values look about the same. Since it is uniform, it doesn't have any modality, so I'm not going to describe any. You might look at this and say, oh, well, the mode's right here. This one's the tallest one at 98, it looks like. But then you look at the bar for 100, and they're not that far from each other. They're not even 1 unit away in height, so I wouldn't call that a mode, because there's one right next to it that's about the same height. And then... Sorry, I just coughed into the mic again, or cleared my throat. So the center looks to be about at 104, 105 maybe. Yeah, that looks about dead center. My spread, pretty much everything's in this range. I'm going to call it 20. That's about what it is. I'm using the range this time instead of standard deviation for funds. If you wanted to actually calculate it, you'd do 116 minus 94 and come up with 22. Good times. Any unusual features? Nope. This one's not unusual at all. How dare you be ordinary? Haha. And now on to 3.6. I like 3.6. Graphs like 3.6 come up a lot. I also love that this starts with B, not A. Oh, typos, typos. Can you get your typos? Why am I singing a song? Okay. All right, let's go ahead and describe this puppy. I would call it uniform. Why is that over there? Oh, because it's going to go on top of this. That's dandy. Uniform. Not uniform. Unimodal. Just one mode. At about 15.2 maybe. We'll come to that again. This looks pretty symmetric to me. I would say the center is at about 15.1. Maybe 15.2. I'm going 15.1. Spread is about, oh, I'm going to have to do this again. 8 million tabs later, I'm in the spot I want to be in. I don't know. I'm going to say like 0.5. If you don't like me doing the standard deviation for this, you can also use range and be like, hey, I'll take the max minus the min, which is roughly 13.4. Sorry, I'm counting boxes backwards, which you can't see me doing, but you would have seen me doing in class, and call this 3.4, which, if that makes you more comfortable, that's perfectly fine to use as the spread. And then for unusual values, I mean, I've got some possible outliers here for sure. Looks like I might have some at 16.8, and on the lower end, 13.4 is possible too. I mean, there is some data nearby it, but, I mean, it's kind of far away. Oh, and then we have a typo. This should not be here. Strike through. That should be median. One of these days I'm going to remember to fix that. Sorry, that error has been there since I started teaching at Northwood, and I never remember to fix it. Aren't I a great person? Oh, okay, so since it's symmetric and I don't have really any extreme values, what values I do have that are extreme are I have on both on the lower and on the upper end. So I'm gonna say the mean and the median are about the same. The mean and median, I keep doing that, are about the same and are both about 15.1 or 15.2. Some of you might have said 15.2 because that's like the box right there. Anyway, here we go. Now for some questions to lead you down the extreme value path. So you look at the values down up above and you're like, the biggest it gets is 16.8, but suppose you missed one. Oops, data entry, it happens. So you go to type in and you're like, oh, it's 25.7. So if you're picturing where this would be, it's probably like here-ish on your graph. I need to giggle less because it's really loud on the mic. Yep. So that's really far away. Oh, I wonder what would happen to the mean. Oh no! So you're probably not gonna like my answer to this as well. So when you look at the mean and you add an extreme value, the mean is going to increase because I have a value that I included that's much larger than mean. Since the mean changed, remember what the standard deviation is doing? It's trying to describe spread or average distance from the mean. It's not too surprising that the standard deviation is also going to increase. Alrighty. And then the maximum, so our maximum was 16.8 and now it's 25.7. So this one's probably the most easy one to tell that it's going to increase. And since my maximum increased, my range, which is just my min minus my max, is also going to increase. So you're seeing how all these values are affected by just one single extreme? That seems rather extreme, doesn't it? Ha ha. Never again. All right. How about the median? It might move over 1 unit. That's it. So it's probably likely to not change at all. And here's where things are going to be a little bit of a kicker. Now the IQR, because it includes Q3 and Q1, might change a little bit, but not much at all. It's likely to maybe have no change, but it might change a little. It might move up a little. So if you're picturing this, I added one data, so my IQR might move up by like 1 unit each. So the Q1 might go up by 1, Q2 might go up by 1, and that might cause a slight difference. Alrighty. Standardizing data. I don't know how I'm going to do this part with typing. It's going to be hard. I hope you're prepared. I'm going to do my best, man. That's all I ask of you. So I'm going to talk to you a little bit about why we standardize and what standardizing is. And then we're going to move on to, I'm going to write the equation for it. So, yep. So first of all, what is this? So it's Z is what it's called. It is called the standard score. Oops, too many hards in there. Or z-score. And is the number of standard deviations, the value x is above, that was very Canadian of me, the mean. Oh, above or below, because it could go either way, sorry. So I'm going to write the equation for this to try to help you out. But just as also a little note, this is also called studentizing, which I think is hilarious. It seems a little weird the first time you see it, but I'm going to now write the equation for this. So Z, oh, that was supposed to be blue because I've been doing everything in blue. Z, okay, that's not working. Hold on. I feel like I've said that a lot in these notes. Z is, this is just equal to the fraction. I have some value of interest, which we call x, minus the mean, so x bar. It keeps trying to scroll when I try to write. Oh, okay, hold on. Let me try this. There we go. Divided by the standard deviation. So remember, just a little polite reminder, you know, mean. and that's standard deviation. So if you're picturing what this is doing, I have a value I'm interested in, I subtract the mean, so that's how far away it is from the mean, and then I divide by the standard deviation. So what this is doing is counting how many standard deviations you are away from the mean. I'm going to give you a little bulleted list of facts about this. So the first thing you want to think about this is it behaves like a ruler. It's how many ticks on the ruler you go away from center. Luke is like a ruler. The standard deviation is our unit of measure. And Z is our number of ticks on the ruler. I know that seems strange, but I'll talk about this again when I see you guys in person, and hopefully it'll be a little better that time. So this gives us a way to compare values on different distributions. I'm going to do an example of this. It's actually our last example, so you'll see how this gets used. So still should be in blue, but nope, it likes to change colors on me. So my example for this is just to kind of give you an idea of why you might want this is in sports, we're often interested in comparing players from different decades. So, like, I'm going to use baseball, maybe comparing like Hank Aaron to Ichiro Suzuki, who's my current favorite player. Actually, I think he might retire soon, so I need to be quiet because I haven't watched baseball in like 5 years. That's bad. I should be careful. But they play in different times with different players under different rules. So they're technically like completely different data sets when you think about it, because the mound height used to be way higher, and where the positions are has changed. Like shortstop used to not be a thing, and it's a lot of the rules have changed. So because of that, you compare them similar to their peers and then ask who's better, and that's how you're going to do this. And it seems a little unusual, but it's totally going to be the way we do this. And the last thing I want to note about this is something I mentioned earlier. So the last thing we're going to note about this is it gives us a way to decide if something is unusual. Remember, we're using X here. Is unusual. And I want to be specific about that. So if your z-score is above 2 or below -2, we call this person unusual. And if you get more than 3 away, you're very unusual. So if it keeps wanting to do the autocorrect to black, it's really driving me crazy. If the z-score is above 3 or below -3, it is very unusual. I can't spell unusual. That was really hard for me. And I mean this. It's very, very unusual. So, so for instance, Ichiro is like a 4.5. He's incredibly unusual compared to his peers. So I'm very impressed by him as a statistician. Not that you guys care, but baseball. I'm sure that goes over well with those of you who actually know baseball, but the rest of you are just like, what on earth is she talking about? Okay. Where's my 3.9 example? It's not on here. Crap. Okay, well, I'll have to wing that one. Let's find some z-scores. So big thing with this, be very careful when you're creating that fraction. It's always subtract mean, divide by standard deviation. So like for this first one, our example is we have some quantitative data with a mean of 57 and a standard deviation of 5. Find the following z-scores for each. So for this one, blue. Z would be 47 minus 57, so that's going to be 10, divided by 5, which will totally give us, oh, careful, negative 10. Don't forget your subtraction. That'll give us negative 2. So this one's a little unusual. It's 2 standard deviations below the mean. Not sure how I got that blue line there, but it's there. We're just going to ignore it. I'm going to assume that was my palm hitting. I thought I had palm cancellation on. I guess I don't. So for the second one, I'm going to do 62 minus 57 divided by 5. Oh, that's 5. So 5 divided by 5, that gives us 1. Yay! So when you're comparing A and B, notice that 47 was below the mean, and I came out negative. 62 was above the mean, that came out positive. I wonder if that's going to stay true. It totally is. So it's like a ruler with positioning and everything. So let's do 59.5. That's the best 9 I've ever drawn in my whole life. Minus 57 divided by 5, that's going to be 2.5, which is a half. Or 0.5 for those of you who don't like fractions. There you go. Don't say I never gave you anything. Let's see what happens at the mean. Come on. I love this thing when it works. And then the rest of the time I'm just sad about it not working. Aha, I'm back. 57 minus 57, so my numerator is going to be 0. Divided by 5 is 0. Oh, so when you're specifically at the mean, you are no standard deviations away from the mean, which is why your z-score is 0. I want to try to fit these all on one page. Let's see if I can do it. So z is 60 minus 57, so that's going to be 3. That's not going to come out nicely. Divided by 5, 3/5, that's 0.6. Good times. All right, z 0 minus 57 divided by 5. Oh, that's not going to come out nice. Negative 11 and a fourth. It's going to be 2/5. Oh man. So the most unusual value on here is that negative 11.4 because it is the farthest from 0. So that value is the most unusual. Okay, so the next example that I have in your notes isn't showing up on my page for some reason, but it's about the ACT and the SAT. Come on, let me change colors because I want to. Because I know this is here for you guys. And I've got like enough time to finish it. Come on. Okay, 3.9. Oh my gosh. So awesome. So I know the example says something along the lines of, okay, the ACT has a mean of 24 and a standard deviation, or sorry, a mean of 20.8 and a standard deviation of 4.8. And the SAT has a mean of 500 and a mean of 100. And then they say that in order for you to get into a certain math class, and I think it's 115, you have to have a ACT score of 24. But if you took the SAT, what score do you need? So to kind of summarize what we know, I'm going to make like a little summary right over here with my pen. So I know about the ACT. Oh, come on. The amount of erasing I'm going to have to do to try to make it so it doesn't seem like I'm insane trying to get this pen to work is going to be just hilarious to me. Okay, so I know the ACT's mean is 20.8. Woohoo. And then the standard deviation, so I'm just going to write an S with a little A on the bottom of it to remind myself this is the one for the ACT because there's 2 of them floating around, is 4.8. And who picked that scale, by the way? That's just ridiculous. And then the SAT mean notice I'm using the bar for mean, just like we should, is 500. I'm drawing with my mouse at this point because I can't get the pen to work again. And then S with a little sub S for SAT, that just looks like I'm writing crazy stuff, is 100. See how the scale on this one just makes so much more sense? And this is the math portion only, not the entire test. And then I know to get into the class I want to get into at Northwood, I need an ACT score, so notice no bar because that's the actual score, of 24. And what I want to find is I want to find the SAT score that corresponds with that. So earlier question mark. I mentioned that what you can do is you can use z-scores to take yourself from one group, like the ACT, to another, to the SAT. So we're going to do that. Got it? So the first thing I'm going to notice is that, okay, my ACT score, or my z-score for the ACT is going to be 24 minus 20.8, woohoo, divided by 4.8. My 4 looks fancy. My 8s look scary. All right, and when you do that, you get a repeating 0.6. Good times. And now I want to find the SAT that goes with that. So I'm going to set up a second fraction. So I've got the z-score that I'm interested in. It's repeating 6. And I'm going to find the SAT score that goes with that using z-scores. So I don't know the SAT score. Set. That's a beautiful T. Minus the mean divided by the standard deviation. All right, so do some algebra. So I'm going to multiply both sides by 100. To get rid of that denominator. Woohoo! Can you imagine trying to do this on your own? It's a good time. So 66.6 repeating, just move the decimal place twice, is the SAT minus 500. Woohoo! And then I'm just going to take and I'm going to add 500. Yay! Oh, forgive me for writing my zeros like this. So the SAT score I'm going to need is above a 566.6 repeating. So as long as you score above that, you get into the class you want, because 24 was the cutoff to get into it in the ACT. I'm hoping you know something about the SAT, as you know, is that score is impossible because you can't get partial points on that one. So you can't get 0.6 repeating points, but it's fun. Cool. So I'll see y'all on Thursday. Have a good day. Hope you stayed dry and cold and warm, not cold things. It was very weird to just talk to myself for like an hour.